Hello, class. Today we are going to learn the integral test and p-series test. Um, as it states, the integral test, the function has to be decreasing, continuous, and positive. So to remember it, maybe you could think of dogs cuss in prison. Um, and so if the function is decreasing, continuous, and positive, and you see that the summation goes to infinity, a number to infinity, then if you can get an integral from 1 to infinity, again, that has to be an improper integral. If that integral converges, then the summation converges. And same thing with if this integral diverges, then that summation diverges. There's a couple special notes that I need you to be aware of. This does not mean that the series converges to that what the value of the definite integral is. Um, so even though we will get a number on this integral if it converges, that does not mean the summation converges to that number. Okay, so don't think that. Also, the function needs to only be decreasing. Um, so, for instance, if it's a decreasing continuous and positive, the function cannot ever go up like that. Even though it might pass the nth test for divergence, which means the limit to infinity goes to zero, um, it has to always be decreasing, continuous, and positive. And so it's also said to be a word called monotonic. All right, so monotonic uh, is a name that we use in the math world for a function that's decreasing, continuous, and positive. I'm not worried about this stuff right now. We will get to that stuff later. So on example 11, we have a summation from 1 to infinity of n over n squared plus 1. We can think of the other tests that we have. We have GST test, we have nth test for divergence, and we have telescoping test right now. So if we were to do this, we should always start with the nth test for divergence. If I take a limit to infinity of this rule, we get 0. So we need to keep going. It's not telescoping because we don't have a subtraction going on. We can't break that denominator up. We also, it's not GST because it's not in the form of our ratio raised to a power. So we need another test, and that's why we have what's called the integral test. So I'm going to do an integral from 1 to infinity of n over n squared plus 1 dn. So we should notice that our u would be equal to this n squared plus 1, so our du would be 2n dn. So it does get covered, but what needs to go out front is a 1/2. Again, just like we did in 8.8, this is an improper. So technically, if we were to write this out in a free response, we need a limit statement, just like we did last chapter. So we do a limit statement as b approaches infinity. And so then it perfectly covers for what we need. So it'd be a natural log of n squared plus 1 from 1 to b. So now when we substitute in b, we're really thinking about substituting in infinity. So we have natural log of infinity squared plus 1. So natural log of infinity basically is still infinity. So now we have infinity, and then minus, we now substitute in 1, so now we have 1/2 natural log of 2. However, infinity minus a number is still infinity, so the integral diverges, which means the summation will also diverge. All right, let's look at our next example. So we have this summation, and so it doesn't fit GST. If we do a limit to infinity, it does go to 0, so it does pass the nth, but we need to keep going with something. So we're going to take an integral. So now we think of it as the integral from 1 to infinity of 1 over n squared plus 1 dn. And so now I just can't do a straight up u substitution like we did before because my 2n won't get covered. And so we need to think of a degree power difference of 2. So it's going to be an arc of some kind, and this one's an arctangent. So I now have an arctangent of n from 1 to b, when I have a limit as b approaches infinity. Again, we need to show that proper notation because it's an improper integral. So now when we substitute infinity, we now have arctangent at infinity, and we should know that it's pi over 2. And then minus, now we substitute in 1, and so now we have arctangent at 1, which we know is pi over 4. So we have pi over 2 minus pi over 4, which is pi over 4. So it converges to a number, which means our summation converges by the integral test. Now, this summation does not go to pi over 4. However, we do know that this sum will add up. I should probably go back and say on example A, this diverges by the integral test. All right, if you notice on your notes, example 12, I am skipping. So now we're going to talk about p series. Now, we have seen this before with our p integrals, and it's very similar. So if we have 1 over n to the p, sometimes we have to manipulate it to get it in that form. We have a p series. Now, when our p is 1, it is a special series, and it's called a harmonic. All right, we'll talk about that one as we go along. So, for instance, if we substitute in 1, we would have a harmonic for my p. However, a harmonic series diverges. And then if p is less than 1, again, the series diverges. And if p is greater than 1, the series converges. Again, just another note, if the p series converges, we can't find its actual sum. We can find its partial sums, which we do with most things, except for GST and telescoping. We can actually find the infinite sum. All the other ones, we just find the partial. So let's look at some examples. So we're going to figure out if these following converges or diverges. Now, we need to manipulate it a little bit. Again, you can use the nth test for divergence if you want to just check it. So does my limit go to 0? Yes, it does. So we need to keep going. So we need to kind of rewrite this thing. So now this would be 1 over n to the 3/2 power. And so my p is greater, so 3/2 is greater than 1, which means this converges by p series. In part B, if I were to do an nth test for divergence, my greater power is actually up top, and so the bottom power is actually smaller. So this one actually fails. So this one diverges by nth. Now, there are a lot of ways to Tampa. You could also rewrite that as like a summation of n over square root n is really square root n as we go from 1 to infinity. So again, if we were to do an nth test, that one diverges by nth. So that one's not even a p series. Now, if we look at part C, if we substitute in infinity, my higher power is on the bottom this time, so this does go to 0. But that doesn't mean it converges, so we need to do another test. So let's manipulate this a little bit. So if I have square root n over n, this is really 1 over square root n, which I'm going to call n to the 1/2 to show you. So I now have p is 1/2, and is p greater than 1/2? No, it's not. And so this one diverges by p series. So this one passed the nth test for divergence. However, it failed by the p series test. So this one diverges by p series. It doesn't go to 0 fast enough. All right, let's look at part D. You don't have to manipulate this one at all. I have a large number as my numerator. However, my denominator, I have n to the 1.1. So is that exponent greater than 1? Yes. So this one converges by p-series. All right, so your homework is day 1 of the homework packet that you have on Canvas. So we're going to take a break from the book for just a little bit and then go into the day 1 homework packet. This will include all of these tests. So the first thing we should always do is the nth test, and that's a limit to infinity. And if it goes to 0, we got to do something else. If it doesn't go to 0, it goes to infinity or negative infinity, we know it diverges. GST test. So the geometric series test, we should figure out what our ratio is. And if that absolute value of the ratio is less than 1, it converges. And how do we find the summation on that? We use a sub 1 over 1 minus r to actually find its sum. Telescoping, a lot of the times you need to use partial fractions. Sometimes it's already set up for us, but that's when you go term by term. And figure out when things cancel. And then at the end, do a limit to infinity of that term that will not cancel at the end. And then we actually get a sum, an infinite sum on telescoping. An integral test is when these other ones don't work. We try to take an integral of it. And most of the time it will be improper. Actually, all the time it will be improper. So then if we can actually converge the integral, then the series also converges. If the integral diverges, the series also diverges. And then p-series, when we have our fraction of 1 over n to the p, if p is greater than 1, the series converges. If it is less than or equal to 1, that series will diverge. If it is 1, it's kind of a pain, but it's a harmonic, and we'll talk about more of that special case. I hope you have a wonderful, wonderful day, and I will see you guys on Friday.